Okay, so what we are looking at in the last class is this idea of generate and test. So the idea here is to, um, so this is a design pattern for logic programming. The idea is to generate a candidate solution and then actually have a test which tests whether the solution, that the candidate solution that we've generated, satisfies the property that we are looking for, right? So this is a design pattern for logic programming. We'll sort of see why this is useful and various ways of using it for some interesting examples. That's what we'll do, right? So the idea itself is quite simple, but we'll see the applications of this idea in multiple examples. Okay, so this is a famous problem that was formalized by Dijkstra. Um, I hope you know who Dijkstra is, right? So Dijkstra invented many of the core algorithms and ideas that we that underlies current computer science. And he also happened to be a Dutch person, so he invented this problem called Dutch national flag. So the problem itself is very simple. Okay, so given a list of colors with red, white, and blue, return a list such that all the reds are at the first, and then followed by white, and then followed by blue, which matches the Dutch national flag. Right? So this is essentially a sorting problem. Um, so we know how to do sorting. So this is a different way of um, achieving the same solution, but the methods are going to be very different. Okay, so that's the idea here. Um, yeah, okay. So we are going to use generate and test for this. So we have a procedure for generate, right? We generated this idea of permutations, right? That is the generation procedure, and the test procedure is the correctness of the condition that we want, right? The condition that we want here is that in the given list, there must be all reds followed by all whites followed by all blues. So we will implement this as a test. I will, and the way we will do this is we will implement this predicate called check flag that takes a list of colors and then checks whether they are in the order red, white, and blue. So the way we've done this is check flag. Um, check flag is a clause, is a rule that holds on some list L if check red of L holds, right? And check red of L holds if the head is red and check red of tail holds, right? So you sort of like pop one red element out. And we also need to transition to this checking the white. So check red also holds if the head happens to be white, right? And for the tail now, this predicate called check white holds. So we are now off to checking whether the rest of the flag is well formed, right? Check white of T holds. So similar idea for check white, right? So check white holds if the head of the list is white and the tail of the list happens to be satisfying check white predicate. So this is going to keep checking, be accepted for multiple iterations of whites, right? Multiple occurrences of whites, and we need to transition to blue. So check white also holds if the head is blue and the tail happens to satisfy check blue predicate. And similarly for check blue, the head has to be blue, the tail has to satisfy check blue. So this will keep consuming multiple blues and the flag should end, right? So check blue of empty list also holds, right? So essentially what we're doing is we are describing a state transition system, a state machine, right? So which recognizes reds followed by whites followed by blue. So if you run this and you check whether this flag is well formed. So assume that this is the flag, right, which has red, white, and blue. It is going to return true. But if you have white, red, and blue, which is not a well-formed flag, which is not a well-formed Dutch flag, it's going to return false. Okay, so that's the idea here. So this is basically checking whether the given list is well-formed. So here is a short quiz, right? So here is a quiz. So this is the same predicate list as defined earlier. So these three queries. So you can of course, provide your answers in the chat window. Two of these are easy. One of this is maybe a little bit tricky. Any answers? So I'm going to check flag. Okay, all true. Yeah, so I think many of you have gotten this right. True, false, false is the answer, right? So really, the way to solve this problem is ask the intuitive question, right? The intuitive property that we are solving is Dutch flag. Check flag is does not have any colors at all. So it's going to go to check red. Check red, if you look at check red, right? Check red predicate, ignore the colors for a moment. Check red predicate only works on, it unifies with the goal that has at least one color in the flag, right? So this particular third one is going to return false because we cannot unify a empty list with a non-empty list. So that is going to return false. For check flag blue, you see that the colors are red and white here, right? Why am I doing this? Check flag goes to check red first. So there is red and white. This is going to fail, right? Because blue doesn't unify with red or white. These are just atoms. But this one is a little bit interesting. So check flag white, blue, right? If you look at these two, there is a white here, check red of white. And this goes to check white of T, which can of course satisfy with the check blue of T. And check blue of T has a empty list that precisely satisfies the first one. So the answer, as many of you have correctly got, is true, false, false. But this is not desirable, right? So we really want a Dutch flag. If you just have a white and blue, it's not a Dutch flag. How do we fix this? The way we fix this is we add one more state in the state transition system, right? Basically, we have a gatekeeper which makes sure that there is a red color before you can actually go on to white. So, so I introduced this idea of check red and check red too, right? So check red is a predicate, which is what check flag calls into. Check red has only one clause, right? And the only clause says the first color has to be red and the tail has to satisfy check red too, right? This is just a gatekeeper there. And check red 2 is the same as the previous check red, right? It consumes multiple reds and one white and goes on to check white, consumes multiple whites and then goes on to blue, and everything else is the same. The only difference is this idea of splitting this red into two separate states. Okay, so now if you do white blue, it returns false because check red has only one rule, and the head of the rule unifies only with a list that has red as the first color. This one doesn't. Okay, so this is the checking procedure. So we are going to use CHK flag for our checking procedure. Right now, the question is the original problem said, okay, I will give you a list of colors, and you have to give me a list that orders the colors in the right order. Right, and the way we do this is using permutations, right? We use permutations to generate one of the possible alignments, and then we check whether that particular ordering satisfies the check flag primitive. So make flag takes a list of colors, right, and then returns you a flag F, which is one of the permutations of the given colors there. And basically, this is just what I said. So it permutes the input with some F, right? It permutes the given list to get some list which is F, and we have check flag of F, which is just a test, right? So if we can generate one permutation that satisfies check flag, then we are done, right? So now, of course, this has many answers because blue and blue are equivalent. So if you reorder these, you'll get the same answer. So that's why I limit the results to 1. But here the idea is that I have white, red, blue, blue, blue. So the answer would be red, white, blue, blue, blue. So which is what I have here. So this is the key idea behind generate and test. So you permute the input to generate a candidate solution, which is F, and then you check that the candidate solution satisfies the property that you're looking for, right? And yeah, and as you can see, right? So um, this is sorting. So we are sorting the colors according to some predetermined order. You can yeah, so this is what I mentioned, right? So generate a solution, test if it's valid. If it is not valid, then Prolog automatically backtracks and tries another solution because permutation gives you all the permutations. So that is why it works. And if you stare at it, the problem is the same as sorting. So we can define a sorting procedure, a permutation sort, which sorts the input list of numbers, right? So here is the sorted property. So as usual, what you have to do is to define a test for sortedness, and then we'll use permutation to generate sortedness. So testing sortedness is much easier than actually generating the sorting procedure, right? I'm not claiming that this is efficient for sorting because we know that there are other efficient procedures, but this is just to get the point across. Okay. So when do we call a list to be sorted? An empty list is sorted, right? A singleton list is sorted. A list which has at least two elements is sorted if A is less than or equal to B, and the tail of the list here, right, which is B appended to tail, is also sorted. So this is the procedure that you would write, say in C, if I were to tell you to write a procedure which says, given an input list, check whether it is sorted. Right? So we have this sortedness procedure. So that's done. Now we can actually check whether something is sorted, right? Just to get the point across. 1, 2, 3, 4 is sorted. So that goes through. 1, 3, 2, 4 is not sorted. So that is false. So here is a sorting procedure that uses permutations, right? So given an input list, this predicate perm sort holds. The way to read this is predicate perm sort holds if given an input list, SL is a permutation of the input list and SL happens to be sorted, right? And this is precisely what we have written down here. So SL happens to be a permutation of L and SL happens to be sorted. So if you do this, then here is a simple example, which is 1, 3, 5, 2, 4, 6, which is not sorted. And then you can sort it using this procedure. So, so this works out, but this is not the most efficient sorting procedure. It's a terrible idea, right? We know we have better idea for sorting. A better approach would be to divide and conquer. So this is, and you want n log n running time, don't you? So divide and conquer gives us the n log n running time. And just to make sure that you don't get the wrong idea that sorting is like a terrible procedure in Prolog, I'm giving you quick sort. This is a bit of a digression from generate and test. So this is just a illustration of how you can do efficient algorithms, right, in Prolog. So what we are going to do is to implement quicksort, which we know is an efficient sorting procedure. So we are going to partition the input list into based on a pivot, and then we are going to sort the sublists and append them together. Right? This is what we are going to do. So in order to do this, we need a procedure called partition, right? And the partition predicate says that given a list L and an element X, which is the pivot, it gives you LES, which is the list of all elements which are less than or equal to X from L, and GS, which is the list of all elements which are greater than X from L. Right. So this is partitioning the input list into less than or equal to and greater than. Right. And how do we write this procedure? So if the given input list is empty and you have the pivot Y, then the partition is going to be empty, empty. So that's easy. So let's say the given list has a head X and the tail XS, and the pivot is Y, right? If X is less than or equal to Y, then X must be in the in the less than or equal to list, right? So X will be part of the less than or equal to list. And RS is some list. So LS and RS is not defined here. They are defined as part of the recursive call, right? So you basically say if X is less than Y, then X must be in the less than or equal to list. And how do you get LS and RS? You recursively call partition on the tail of the list XS, right? So XS is the tail of the list. You partition XS such that all the elements less than or equal to Y is in LS and greater than Y is in RS. And once you get that, you can just cons X to the front of the less than or equal to list. So this is for the less than or equal to case, and for the greater than case, you do the same thing, right? If X is greater than Y, then X will be part of um, X will be part of the greater than list, and we have a condition here which checks whether X is greater than Y. Okay, so this is partition. So to give you an example of partition, this is the input list, right, which has some list of numbers, and then you have the pivot to be 4. We want X and Y. So all the elements that are less than or equal to X are in 4 are in the X list, and elements greater than 4 are in Y list, right? Okay, so now that we've defined partition, we can easily define quicksort. So quicksort is the procedure, right? What do we want for quicksort? Quicksort holds. Basically, the way to read quicksort is given an input list. Quicksort of that is going to be the sorted list SL. Okay, so that's the reading. Sorting an empty list gives you an empty list, right? Sorting a non-empty list with the head H and tail T gives you SL, right? Where you pick H as the pivot, right? Partition the tail into LS and RS. You recursively call a quicksort on the less than and greater than, right? So if you quicksort LS, you get sorted LS, SLS. Quicksort the right hand side list, you get sorted RS. So you've got sorted sublists. All you need to do now is to append it such that the pivot sits in the middle, right? So which is what we are doing here. So SLS pivot cons to the RS list, and you get a sorted list. So this is a natural description of the quicksort algorithm, and here it just works fine. I mean, this is efficient, right? So this is doing divide and conquer. So of course you can do these sort of algorithms. So let's any questions on this so far? This is a digression, right? Quicksort again. Quicksort doesn't use generate and disk. I just want to show you an example of doing quicksort in Prolog. Okay, if there are no questions, let me proceed. So have you heard of the n queens problem? The idea is that you'll be given n cross n chessboard. N could be any number, and you will have to take n queens and place them on the chessboard such that none of them threaten each other. So you know the rules for the queen, right? So queen is threatening another queen if they are in the same row or the same column, and diagonals also, right? So diagonals also shouldn't have any threatening positions. So for and you can generalize this for any n. So you can sort of say you can give it any n, and there might exist a solution. There might exist many solutions. There might exist one solution. But the idea is to find such assignments. Okay, so that's the goal of this procedure. And typically this is done for 8 cross 8. Yeah, so this is a problem for which backtracking is the right way to do it. So you sort of place one queen at some position. You then try to place the next queen in some other position. If they threaten, then backtrack and then try the other position. This is precisely how to solve this problem idiomatically. And Prolog is best placed to solve this because backtracking and choice points are built into Prolog, right? So if you were to implement this in C, you would implement backtracking and choice points, right? So that's the point that I want to get across in this example. It is these error problems are very natural to express in Prolog. Okay, so here is the idea behind the implementation. So one thing that you really want to do is, if you think about generate and test, right? It is generating lots and lots of positions, and then it is checking whether that position is safe. So if you want to make generate and test efficient, you must think about a good representation that rules out invalid states by construction, right? So this is, I mean, this idea is sort of succinctly captured by this term called make invalid states unrepresentable. Um, I think this quote is attributed to Ron Minsky, who is one of the managing directors of Jane Street. So he mentioned this as part of why OCaml is nicer, right? Because you have algebraic data types, you can precisely define what states are allowed. And by making other states not even possible to write down, you don't have to consider those states. And this nicely applies here. So what we will, so the application of this idea here is that what we will try to do is to um, avoid having a construction where queens are on the same row or the same column, right? So we won't even generate a candidate solution where the queens are in the same row or the same column, right? So that's the design principle that we'll start with. So by not even being able to represent a state where a queen may be, two queens may be in the same row or the same column, we are not even going to generate those states. We make the generation procedure very efficient. Okay. So this is what we are going to do. This is where mostly, if you sort of have a good data structure, right, the algorithm becomes much simpler to implement. And this is one example of that. So here is the representation that we use for the position of queens on the board. Okay. So we represent the position of queens on the board as a permutation of 1 to n. So if I'm solving this for n cross n matrix, I will say that the assignment, a candidate solution, is going to be a permutation of 1, 2, 3, 4 up to n. And the way to read this is each number represents the position of the queen on that row, right? And 1, 2, 3, 4 up to n says that the first queen is on 1, 1. The second queen is on 2, 2. Third queen is on 3, 3. Fourth queen is on 4, 4, and so on, right? So by having one queen at each row, we rule out the case that two queens are on the same row, right? And by having this as a permutation of distinct numbers 1 to n, we avoid the case that two queens are in the same column, right? So if you want to represent two queens on the same column, these numbers should repeat. By ruling out that any number, any permutation of this, right? Any permutation of this list is if you interpret that as a position of the queens, then two queens will not be on the same row or the same column, right? So we've ruled it out, but not every solution obviously is a correct one because this solution is wrong, right? So if you think about this, the first queen is on 1, 1, the second queen is on 2, 2. The first queen is threatening the second queen in the diagonal. Actually, it's threatening all the queens on the diagonal. All the queens are on the main diagonal in the chessboard, right? So this is not the solution. But if a candidate solution exists, it will have to be a permutation of this particular list, right? So that's the key idea here, which makes it work, right? Now all we have to do is the usual thing, right? We generate permutations. We need to implement a test which checks whether this a permutation of this list is a valid assignment. So we have to check whether queens threaten each other in this, right? So the way we do that is we implement a procedure called the checkboard, right? Checkboard takes a list and returns true or false. And the idea here is that this 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 is going to check whether the positions are valid. So what we are going to do, the high level idea is that we will iterate through each row, right? And for each queen on that row, we will check whether the outgoing the diagonals this way. So for the first queen, we will check whether this diagonal does not have any queen. This diagonal does not have any queen. Of course, there is no possibility of queens here. But the outgoing V, right, the upward facing V does not have any queen. So we will do this for the first queen. If that is okay, we'll do this for the second queen. If that is okay, we'll do this for the third queen and fourth queen and so on. So for the board, we are going to iterate through each row. For each of the row, we are going to take the position of the queen and we are going to check whether the upward V does not have any queen, right? So this is the intuitive idea. The procedure itself is just translation of that idea, right? So what do we do here? Checkboard has two predicates. So if the board itself is empty, then the board is safe, right? The length is 0, so it is safe. It is going to be used because we are going to keep checking rows. So the important one is this checkboard rule here, which says, okay, H is the position of the current queen at some row. Now you need to check the upward facing V, right, for the tail. So we are going to look at the tail and we are going to see whether the upward facing row is void of any queens. So we are going to do that step by step. So if I'm considering the row 1, right, for the row 2, the upward facing V is um, the next, both the previous column and the next column, right? So this one and this one. So which is what I'm computing by having L as H minus 1. H gives me the position of the queen. L is H minus 1, which is this position. And R is H plus 1, which is this position, right? And I check queen here. So what I'm going to do is to call check queen, which takes the current position of the queen on that second row and checks whether the queen is not on L, the queen is not on R. So this is not equals, arithmetic not equals, right? Just so that we understand the syntax. This basically means H is not equal to L, H is not equal to R, right? So if both of these hold, so what do we know? We know that in the next row, the queen doesn't threaten, right? The position of the next queen is not threatening. It is in some other row. In this case, it happens to be on the column F here. So we have to repeat the procedure for the same idea, right? So if I checked L minus 1 and H plus 1, for the third row, I have to check L minus 2 and H plus 2 here, which is what I do here with the recursive call. So I say L next is L minus 1, R next is R plus 1, right, here and here. And I check that the next queen, the third row's queen, is not in that position. And you keep doing this over and over. So for a given queen, this check queen checks whether there is no threatening queen on this V. And checkboard basically goes through and checks for the tail of the list. Right? So this is the inner loop essentially, and this is the recursive call to the outer loop. And the inner one is also a loop because the check queen calls another check queen. So there are two for loops essentially, and that's the procedure that we want. Right? So this is checking whether the queens are in the correct positions. So here is a satisfying solution for this one. I think this is capturing this assignment 1, 6, yeah, 8, 3, 7, 4, 2, and 5. And this is a valid assignment. So checkboard of this assignment gives me true. Any questions on this one? How we encoded this one? Okay, looks like there are no questions, so I'll continue. So we've designed the test procedure, right? Now we have to design the we have to combine the permutation and the test. So um, for n queens, we need to solve for arbitrary n, right? And the starting solution is a list from 1 to n, right? So we write a simple procedure for generating a list from 1 to n. We use this procedure called make list, right? So the idea is that given some n, it forms the initial assignment, which is 1, 2, 3, 4 up to n. So if it is 0, then just return an empty list. If it is some n, which is not 0, which is, it could be 0, but it doesn't make sense here. If it is n is greater than 0, then consider m to be n minus 1, right? Make an initial assignment for m, which is 1 less. That's the recursive call. And then append the n to the end of the list, right? So you will get an assignment, which is, if you say n is 8 here, you will get 1 to 7 here. And for 1 to 7, append 8 to the end. So what you get is 1 to 8, right? So if you do this and run this, you will get the assignments 1 to 8. So, okay, so given that, now we can actually solve n queens. So the point of n queens is given any n, we are going to get the board assignment for that n. And the way we do that is we first generate the initial assignment for the n. We permute the assignment, right? And we check whether that particular assignment satisfies the board property, right? That is n queens. So here is one solution for n queens, right? So give me a solution for 8 queens problem. Give me the board assignment for that. So if you run this, then you get one assignment here. Actually, there are, if you look at Wikipedia, there is 92 solutions for this 8 queens problem, right? For 8 queens, there are more and more as you sort of increase the board size. You can get all 92 with the same procedure. You don't have to do anything because Prolog has built-in backtracking and choice points, right? So all we need to do is to ask this and you'll get all the solutions here. I'm not going to go through this, but you can check that these are the solutions that are all valid solutions, essentially. So these sort of problems, right, which are backtracking and exploration, these are very naturally encoded in Prolog compared to other languages. Any questions on this one so far? Okay, so that is all I have about generate and test. So let me move on to the next lecture, which is going to be on cuts and negation. Okay, so the title of this lecture should sort of kindle some interest in you because written negation here. One thing that we sort of mentioned early on in when we studied the logical foundations of Prolog is that we don't have any way of representing negative information in definite clause logic, and that's why every program has a model. So this should sort of bring in some questions in your mind, and we will see what those are. Right. So previously we saw generate and test. Today we are going to see this idea of cuts, essentially. To give you a one-line summary, Prolog is not a pure logic program, right? So it does SLD resolution. So it basically picks the goals in the order in which they are written down. That's the rule order, and there is also the goal order. So you pick the leftmost sub goal to satisfy before you move on to the next one. So you have this search tree, right? There is a deterministic procedure for going through the rules. and you get choice points essentially. And cuts in Prolog are this extra logical mechanism. So they are not pure logic. They are a way to prune Prolog search trees. So to place it in, make it more obvious, they are a mechanism for erasing out certain choice points. And it is quite useful for making your programs efficient. But you can also express properties which are not expressible just by pure Prolog without cut. So we will study the idea of red and green cuts. Green cut is going to, again, just to give a summary, green cut is taking the existing Prolog program, using a cut to make it perhaps faster, right? Red cut is actually changing the meaning of the program using a cut. Anyway, so that that's the intro to this lecture, and so we'll motivate why we need these cuts at all. Okay, so here is a simple interpreter, an evaluator for arithmetic expressions, right? And the arithmetic expressions that I have are plus AB. So we can construct terms which are plus AB, which means that A plus B. And you can have mult AB, A multiplied by B. And you can have ordinary constants. Okay, so 1, 2, 3, 4, and so on. So the way we are going to evaluate this, eval is the interpreter function. So it takes a term, right, an arithmetic expression, and then it's going to produce a integer value as a result. That's the intuitive meaning of evaluating that arithmetic expression. So what does this do? So eval of plus AB is C. If you evaluate A and you get the value VA, VA is a number, right? Evaluating B, the arithmetic expression B, gives you the value VB. And VA and VB we expect to be numbers, and C is going to be VA plus VB, right? And similarly for multiplication, evaluating A is VA, evaluating B is VB, and C is VA times VB. And for everything else, we just say eval A wholes, right? So this is expected to match with constants, right? So if I say plus 1, 2, the idea is that 1 will match this one, you get 1. 2 will match this one, the same rule, you'll get 2. And plus 1, 2 gives me 3. That's the idea here. Of course, the point of having this introductory example is that it is going to be broken, and we are going to fix it. Right? So we'll see how to fix it. So we've added 3 clauses. So here is the idea, right? So I have an arithmetic expression here, which is the same as 1 plus 4 times 5, right? It says plus 1 mult 4, 5. And if you ask for the first result of this, it gives me 21. So 20, 4 times 5 is 20, plus 1 is 21. But if you ask for the second result, it says the important one here is, and this is an arithmetic error. So you can run this in the SWIPL interpreter and find that this is an arithmetic error. The problem here is that if you sort of look at this goal, right? This fact, our intention was that A will be a value, a constant, an atom, and if you give an atom, it will be an atom, right? That is what we expected. But the point is, because A is a variable, it unifies with anything at all. It unifies with any compound term, and in particular, when we happen to call eval on this one, even this term, right? This whole term unifies with A, right? And our program says that if you evaluate this compound term, if you unify with this goal, the result of evaluating that compound term is going to be the same thing, the compound term, which is plus mult 1, plus 1 mult of 4 times 5. In particular, this occurs in the recursive call. So, so it turns out that we will get a call where we will try to evaluate mult45, which is the mult45 here, and the result will be mult45 because of this particular fact, right? And as we know, right, when you get a non-arithmetic, non-numerical term here, so this is computation is going to fail. Actually, plus is going to fail as well. So it is going to numerically evaluate the term here, but because of our fact here, we get an expression here which is not what we want, and that fails, right? So that is the reason for this failure here. So the question is, how do we fix this? So one way to fix this is to actually introduce a function called value, right? And the idea of a value is that you wrap all of the constants in this constructor called value, right? So you imagine this function value to be a constructor, and you say, if I have to use constants like 1, 2, and so on, so you wrap this with value, right? And we change the evaluator. The only rule that changes is this rule. We say eval2 of value of a is a. If you give me any other expressions, this won't unify, right? And we have to rewrite the example this way. So rather than directly using the constants 1, 4, and 5, we have to wrap it in value of, we have to wrap it in this function, value of 1, value of 4, and value of 5, right? Now, this term, which is mult AB, does not unify with value because the top function symbols are different, right? So this one works fine. So there is only one solution for this. So it gives me 21, right? So, but if you sort of look at this, this is undesirable, right? We are sort of wrapping constants with function just so that the unification does not causes any issues. The observation is this, right? We know that Prolog picks the rules in the order in which they are written down. If you've unified with if you've unified a particular term with plus AB, this head, you shouldn't go ahead and unify this with a value, right? And similarly, if you've unified with mult, you shouldn't have to unify that with value because sorry, it says value here, but you shouldn't go further because there is only one rule that is applicable. So one way to actually say, tell Prolog that if you happen to unify with this head, don't go and look for other choices, because if you look at other choices, then you're going to go wrong, right? And the way to express this is this idea called a cut, right? Cut in Prolog is written down with this exclamation mark, right? So this is a goal. You read this cut as a goal, but it is extra logical. It is outside of pure logic. The idea is that it prunes the search trees, right? And in particular, it prunes the search trees according to two rules, right? When you come across the goal cut in a rule, right, it is going to have two effects. All the subsequent choices, like the branches in the head of the rule, in the rule where it appears, all the subsequent choices are erased, right? And all the possible choices in all the preceding subgoals. So you might have multiple subgoals, and cut might appear somewhere in the middle of the body of the goal. So all the possible subsequent choices in the preceding subgoals are also erased in the same rule, right? So it only applies for the same rule. I mean, this is a bit abstract, but we'll see more and more examples as we go along. But this is the precise description. We'll see how cut can help with our evaluator, right? So I am writing down an evaluator eval3 here, right? This is the same as the initial eval1. Observe that I am no longer using the value function, but I have introduced cuts here. And the way to read this is that if a goal unifies with the head of this rule, right? The natural behavior of Prolog is to go ahead and say, okay, I will now try recursively the body of the rule, right? All of the subgoals in the body of the rule. The first subgoal happens to be cut. The idea is that if the control crosses this cut and goes on to the next sub goal, one effect that it has, which is what I defined here, is to rule out all possible branches in the head of the rule. If there are other possibilities for matching, right, then you sort of rule out the rest of the explorations here. And the net effect of what is happening here is if if the given term matches plus, then you will not explore the rest of the rules, right? If a given term matches mult, because we have a cut here, if you cross over the cut, you will not match with eval AA, right? And only if you don't match with unify with plus and you don't unify with mult, will you actually unify with this particular fact, right? So what happens here? So you have eval 3, right, which says plus 1 mult 4 5. So this pattern, this unifies with the head here, and you cross the cut. So in without the cut, you would also have another possibility for unification, right? This whole term could be unified with just A here. This goal unifies with this fact, but because we have a cut here, we no longer explore it. And similarly, for the recursive call, where you will have mult, right? Because you have a cut here, if you cross this cut point, you are no longer going to go ahead and try the rule here. So the only possibility for matching this fact is constants, right? Because constants don't match with either plus or mult. They are the only ones that match here. So that works out. So if you do cut here, so we only get one answer, unlike the initial case where we had more than one answer and that failed. And here we only have one answer, and it happens to be in a natural form, right? Cut is sort of pruning the search trees to give us the answer that we want. Any initial questions on this one before I proceed? Yeah, it is. It is extra logical because it has side effects, precisely because it is ruling out a certain choice points, right? And choice points and all of this, if you look at the abstract interpreter, it didn't talk about choice points at all, because it was naturally encoded in the non-determinism that is available in the interpreter. But in order to even explain cut, you cannot use that abstract interpreter, because abstract interpreter is non-deterministic, and cut is precisely ruling out a particular search tree, which is based on a procedure. So, of course, yes, we call it extra logical because of its side effects. Any other question? Cut is a bit weird, so you have to be careful when you use cut, because it is pruning search trees, right? So you'll see some, if you put cut in a wrong place, you'll see some weird behaviors. You'll look at a bunch of weird behaviors that sort of prep you for what you can expect with the cut. Okay, so what is the second point? This point. We haven't come across that one yet. We will see an example in the subsequent slides. I've only shown you examples of this one. This cut is at the first position, right? So we don't have any preceding subgoals. We'll come to that. Okay, so I think this example succinctly captures all cut. So this is a very simple. This is meant to be just a way to explain the behavior of cut. So there is a fact called PA, there is a fact called PB, there is a fact called RC, right? And there is a rule that says QX holds if PX holds and there is a cut here, right? Let me clear it so that I don't give away the answers. So, and then we also have QX, which says QX holds if RX holds, right? So if you sort of stare at it, what is going to be the result of QX? So I query QX here. I haven't actually explained the second point, which is what Venkat was asking, but give it a try. What will be the result of this particular query? Yeah, so yeah, yeah, so exactly, right? So yeah, so let me go through this step by step, right? What happens with QX? So it goes through the first one. Actually, let's go through it. I think the answer might be interesting. So we have QX that matches with the first goal here. Okay, that's fine. And it goes to PX, right? And PX says, so it recursively goes ahead and then finds A. So PA matches, X unifies with A. Of course, there are more possibilities for QX and more possibilities for P as well, right? And if because we have a cut here, it prunes out both of these choice points, right? There is a choice points here which allows the cut to proceed to the next one. There is a choice point here because um, this X is unified with A here, but X can also unify with B. That is also cut. So if you run the result, it's only A because the presence of the cut here both prunes out the choice point in the head of the rule and choice points that are possible for the um, preceding subgoal. So this is precisely what Venkat was asking earlier, right? So this prunes out the preceding subgoal as well. So as a result, you only get A. Let's look at one more example. So this is a so the second example is the same one. I just renamed everything. I just moved the cut to before this call to P. Right? I call it P2 here. So what will be the result of this one now? So the presence of cut here, yeah, so A, B is the answer, right? So the presence of the cut here rules out further exploration for this goal, right? So um, we won't go into the second rule, but cut is before P2, so we will explore both A and B. So the answer will be A and B. Just to complete the argument, if you don't have the cut, actually I need to restart it because prologue will get confused. So if you don't have the cut, then you can see that the answer will be ABC, right? The presence of the cut here, we restart the kernel. Um, the presence of the cut here rules option C, right? And if you understand these two examples, right, you've understood cuts. You'll use cuts to construct interesting patterns, but it's important that you understand how these two examples work. Yeah, okay, so I'll stop here. Questions on this so far? If you have any questions, I'll wait for a minute and then we can stop. Try it out. So see whether the idea matches, right? So as you said, right, there are only two rules here. So see whether the understanding matches the examples that you want to try. I'm sort of deferring it because I can't answer it off the top of my head. Uh, anyway. Any other questions? Okay, good. So I'll stop here and then we will meet on Friday. Thank you.